4.2, we're kind of taking the previous section where we learned about exponential functions and logistic functions, and now we're going to apply those to real-life situations. So that's called modeling. It's not like you're taking exponential functions and logistic functions out on the catwalk. Okay? We're going to be modeling real-life behavior with those. Kind of like the logistic equation, bless you, that we did at the end of the previous section. All right, so for real-life examples, our independent variable, the ultimate independent variable, is time, which we usually use a t to represent that instead of an x. So in this section, you won't be seeing a lot of f of x. You'll be seeing more f of t or r of t or something like that, okay, where t is time. So here's example 1. We're starting with an initial value of $100. Man, who wouldn't want that, right? Here's $100. Start with $100. Assuming that that amount of $100 increases by 30% each and every year, write a model to predict the amount A after T years. Does anyone know what it is off the top of your head? Good. I'm glad. I'm glad you don't know it off the top of your head. Because what mathematicians are, if they're anything, they are pattern recognizers, okay? So that's what we're going to do. Let's go ahead and start just looking for patterns by just kind of working out a couple of years at a time and see if we can then infer a pattern from these concrete examples. So t equals 0, t equals 1 year, t equals 2 years, t equals 3 years. By then, maybe we'll have the pattern. So how much money do we have then at t equals 0? $100, right? I'm not even going to put units. You know the units are dollar signs, right? We got $100. At the end of the first year, how much do we have if we are increasing the amount by 30%? Well, it should be everything we had before, right? 100 plus another 30% of 100. So that'll be 0.3. That's 30% as a decimal times 100. Is that true? That's kind of how you figure out tax on a bill, right? You get the subtotal, and then you have the percentage, like 0.825% times that. Subtotal gives you the amount of tax, and then you add them back together. So we got $100 that we started with plus 30% of 100. Now let's go ahead and look for a pattern already right here. I have 100 in both terms, so I could factor out the 100, can't I? And what am I left with? That's 1 times 100, right? So if you factor 100 out, you're left with a 1 plus 0.3. Well, what's 1 plus 0.3? 1.3. Good. That wasn't a trick question. And so what are we left with? We're left with $130. Sweet. I didn't do anything. I just walked away and came back, and I got 30 extra bucks, and now I have $130. How much are we going to have at the end of year 2? Well, it's going to be everything we had the year before, which is $130. But I'm not going to use the $130. I'm going to use this version of it. The reason being, we're looking for a pattern. If we just give integer values at the end, the pattern is absorbed in the final answer. So I'm going to take that number, everything we had before, 100 times 1.3. And to that, we're going to add another what? That's what we had the year before, and we're going to add to that another 30%. So how are we going to show that? Another 0.3 times what? 100 times 1.3. That's what we did before. It's everything we had the time before plus 30% of that same amount, right? Now let's see if we can factor out the 100 times 1.3. If I do that, I get 100 times 1.3. And when I factor out in the first term, when I factor it out of itself, I'm left with a 1. Plus, when I factor it out of the second term, I'm left with 0.3. Well, what do we have there then? We have 100 times 1.3 times another 1.3. What's 1.3 times 1.3? 1.3 squared. Oh, wow. Okay. Sweet. Let's do it one more time. At the end of year 3, I'm going to have everything I had before, which is 100 times 1.3 squared, plus another 30% of that. So another 30% of 100 times 1.3 squared. If I then factor out the 100 times the 1.3 squared, I'm left with 1 plus 0.3. And look what we have now. Now I have 100 times 1.3 squared times another 1.3, which gives us 1.3 cubed. Do you see the pattern emerging? Well, let's kind of work backwards. This is 100 times 1.3 cubed. In year 3, we have 100 times 1.3 cubed. At the end of year 2, we have 100 times 1.3 squared. At the end of year 1, we should then have 100 times 1.3 to the first. And if we work backwards then, at year 0, we should have 100 times 1.3 to the 0 power, which is 1. Do you see the pattern now? The amount at any given time t should be 100 times 1.3 to the tth power. And that is the exponential function. That captures the pattern. All right, we'll stop there for today so you can turn your calculators in. Make sure you clear out y equals for the next class, and we'll see you tomorrow.